Hello and welcome to another video of Dr. Mahmoud Al-Odeh. And in this video, I will be talking about process capability. Okay, let's take a look into just a brief introduction on what is a process capability. What we've done so far, especially in the last chapter, is we looked into the process behavior and we created some control charts that will help us to see if the process in control or out of control. So now these control charts based on the actual performance of a process. However, what we need to do in this chapter here, we need to examine a process from customer's perspective. Process capability, analyze, examine the process, especially the variable data in terms of voice of the customer and voice of the process. The voice of the customer basically is what the customer requirements, what their needs. For example, if you're expecting to receive your food at a restaurant and in no more than 20 minutes after your order, that is one type of the customer requirement. So another example would be if you're ordering laptops and you said, I want my laptop to be between 1 and 2 pounds weight, then that would be the specification. So you set some specifications and the manufacturer has to meet the customer specifications. So the process capability is based on the specifications that given to you from the customers. So the customers, these are the ones who set the specifications. Voice of the process is the process capability, how the process behave. And this is kind of a reply into what the customer want. So again, the customer set certain requirements and the process respond through empirical data as to whether it can fulfill the request or not. Then as a quality engineer, as a quality manager, what you do, you compare voice of the customer to the voice of the process to determine if the process can meet the customer needs or not, and through these process capability calculation. Just ahead of time, I want to tell you that in this chapter, I will be talking about CP and CPK. And these are the two parameters that we use to conduct a process capability analysis. First, you have to do the process capability ratio, the CP, which is basically if it's more than one, so you do the calculation. If it's more than one, then the process is potentially capable of meeting the customer requirement. So the first thing we do is we calculate the CP, and that will give you an indication if theoretically the process will be able to meet the customer needs or not. And then we'll do the process capability index. So the first one is the capability ratio, the CP, and the capability index is the CPK. And we do the calculation for the upper and lower bounds. And if these are both greater than one, then the process is capable and then will be able to meet the customer needs. Of course, these are the calculations that we need to focus, but I want to mention it to you ahead of time so you know exactly what we're talking about. If the process capability ratio, which is basically the first one, the CP, is less than one, then you have to stop. There's no hope that you can meet the customer needs. So that's the first indication is you look into the CP and the CPK, you do the calculation for the CP. If it's less than one, just stop. There's no hope that you could meet the customer needs. However, if you do the calculation and you got it as a more than one, then there is a hope, there is a theoretical, it's potentially, the process potentially can meet the customer needs. And then you go to the CPK, the other factor, the process capability index, and you see if it's more than one, you do the calculation. And if it's more than one, then you will conclude that yes, the process is capable is potentially capable and actually capable of meeting the customer needs. All right, so what we're going to do here, just go over the process capability definitions. Process capability refers to the ability of a process to produce products or provide services capable of meeting the specifications set by customer or designer. So again, these specification is set by a customers or by the designer of the process. Now, what's the difference? Somebody will ask, okay, what's the difference between the process control limits and the specification limits? Specification limits, again, it's set by a customer. Control limits are the voice of the process. Specifications established during the design process or from customer request. Specifications communicate what the customer expect, want, or need from the process. Specifications can be considered the voice of the customer. Control limits are the voice of the process. The center line on the chart represent process centering. The R and S chart limits represent the amount of variation present in the process. Control limits are a prediction of the variation that the process will exhibit in the near future. The difference between specification and control limits is the specification rely on wishes and control limits tells the reality. So again, control limits is the behavior of the process, the actual behavior. However, the specification is the wishes from the customer, what the customer wished to meet. And if you look into this, this process here, in this chart, you will see that the process is out of control, out of the upper control limit. As you see, there's a trend right there. However, it's still within the specification. So that could be a good, the customer might accept that. But however, in the long term future, if this trend continue, then the process will not be able to meet the customer specifications. Another chart that it's not shown here very well, but I want to share with you that the process could be in control. However, it's out of the specification as well. I apologize for the format for these slides. I'm not sure what happened when I presented this, but there could be a process. Here's the upper control limit, and here's the upper control limit and lower control limit. Here's the line, as you see. And as you see, these are still within these control limits. So the process is in control. However, the specification limits is up here. This is the upper specification limit. This is the lower specification. So this process is not capable of meeting the customer needs. Variation is, as you know, we did talk about it, is the output of process may vary from one product to another, from one item to another. Therefore, it is common to provide some specifications and should be defined. If the measured output of the process exceeds the specified limits, the process is deemed to have failed. So these are the specifications should be within the specification limits in order to pass the process. The results of most processes will vary around the center value. So this is where we need it to be. It's okay to have a variation, and this is the natural variation. This is the common cause variation, and we are expecting to see values around the center line. The capability of the process is the spread of result around this value, with high capability occurring when process results group closely around it. The most common measure of this spread is standard deviation and process capability. These both may define as a range between 3 standard deviation either side of the average. So when we study the process capability, we're going to study whether the process is centered or not around the 3 sigma on the right and 3 sigma on the left. Specifications are often defined separately from the process that being measured and without a great deal of consideration of how easily the process can meet them. So this is the one thing that I want to tell you. the upper specification limits and lower specification limits are not calculated. These are given to you. These are from the customers. These are from the design team. So you don't have to calculate that. What you need to do, you need to calculate the CP and the CPK. So don't start to think about what the equation to calculate the upper specification limit and lower specification limit. These again given to you. However, the process control, what we did last time, we did calculate that using specific equations. You could review that chapter in order to find what these equations. But for this chapter, specification limits are not calculated. It's given to you. All right, just a visually, let's take a look into this process A. The process is easily meet the specification. As you see, the normal curve is here and the specification up here and here. So the process is in here. So there's plenty of space around the normal curve. Also for B, there is also process comfortably meets specification limit. There is enough space around the upper specification limit and lower specification limits. Process and C here only just meet, it's barely just meet the specification limit. Any shift or spread in the values that may result in that the process is not capable. Process D does not meet specification limit. As you see, there's some data in here. The data in here and in here as well, and that will result in not meeting the specifications, and that would result in failures. Another example here, let's see, this is the specification. What we're trying to do, we're trying to fit the process, the data inside these specifications. The more clustered the data is, the better. So as you see, this is the CP is 2, which is excellent. However, in here, this is a 1.66. That's very good because we are higher than 1. 1.3 is excellent. This is 1. This is where you barely meets the customer specifications, and you have to be careful because if there's any shift in the data, that would result in failing in the process and not meeting the customer specifications. Another example to make sure that you guys understand what's the difference between the CP and the between the CPK and the process control limits. So the specification limits is the green lines here. That's the voice of the customers. However, the voice of the process is the upper control and lower control limits. So in this case, yes, the process is capable of meeting the customer demands because the voice of the process is less than the specification. Same thing here, you will see that the process of the voice of the process equal exactly to the customer expectation, which will result in meeting the customer expectation. However, we have to be really careful. We don't want to see any shift in the data. In here, the voice of the process is higher than the customer expectation, and therefore there are so many complaints will be happening by the customers where they were not going to be happy about that process. So therefore, it's not meeting the customer needs. Specification limits, the allowable spread of the individuals are compared with the spread of the process to determine how capable the process is of meeting these specifications. Capability analysis, a common process capability measure, the CP, and this is what we call it, the process capability index, indicates how well the process distribution fits within its specification limits, and is simply the ratio of the specification width to the variation width. Therefore, in figure A, B, C, A, B have a CP greater than 1, and C is equal to 1, and D is less than 1. And we're referring to these charts here. Okay, so this is CP is more than 1, this is equal to 1, and this one is less than 1. All right, how to calculate the CP And again, this is the potential, the theoretical capability of a process, and we call the capability index. Some people, they call it the ratio, capability ratio. So this can be calculated by the width of the specifications divided by the 6 sigma standard deviation, the 6 standard deviation. The greater the value is the better. This is what we're trying to fool. This is what we're trying to do. It's having a value more than 1, which means the width of its specification higher and bigger than the width of the 6 sigma, the spread of the process. All right, so the greater this value is, the better. If the capability index is larger than 1, this is desirable. The process is potentially, and how we translate it, how we interpret it after we do the calculation, we have to interpret the result. The process is potentially capable of meeting customer demands. And now if it's less than 1, then this is not optimal, but could be if it's 1 equal, this is not optimal, but it's feasible. Yes, it still can meet the customer demands. However, if the process is less than 1, this is undesirable and reflect the process inability to meet the specification. Stop right there. No need to continue. Then there's no hope of meeting of the process. You cannot do any calculation after this. All right. Now, we did talk about the standard deviation, and we're going to use the standard deviation in here in this calculation. CP equal the upper specification limit minus the lower specification limit divided by the 6 sigma or 6 standard deviation. And standard deviation is something not given. It's something that you have to go to the process, collect the data, and calculate the standard deviation based on the equation that we covered in the statistic chapter, the first chapter in statistic that we talked about standard deviation. And there is an Excel function that you could use to calculate the standard deviation. Also, there is another way for doing it, is you can do the calculation for the standard deviation by finding the average of the range divided by the D2, and D2 is it's taken a value taken from appendix 2. Or you could do the sample standard deviation divided by C4 as well. The C4 is in appendix 2 based on the number of observations. Okay, the problem with a CP is that it does not take into account how the process is distributed. So the process could be capable, but it's not, we don't look into the distribution. We don't know if it's the process centered or not. And it is important that to look into the process distribution and if it's centered or not. So imagine that, look into the garage door that you have in your house, if you have a garage. So as you know, all the garage is designed to fit any car, small cars, I believe. And so, but however, if the car is not, so the CP is basically to see if the garage will fit your car. However, the CPK will see if the process is centered or not. So the car, it could be, it would fit. Yes, we did calculate. We know that it's going to fit. But however, you may shift the car to the right or to the left, which will result that the car is here. And that means that the garage is not capable, and the process is not capable, basically, not the garage. The process is not capable, which is the car, because you're not going to fit there. Again, one calculation is to see the width of the process, whether we can potentially meet the customer needs, and the other one is when the process is centered or not. So we need to make sure that the process is centered, so it would be easily fit into the specification limits. So one is the capability, the potential, and the other one whether the centered or not. So this is where the second measure, the CPK, need, but with considering only the variation on the half of that closest to the specification limit. Thus, the CP and the CPK, both of these calculations taken given this given as a measure of both potential and centering the process. So one is the potential of the capability, is it capable or not? And the other one is the actual, the center, is the process centered or not? All right, to calculate the CPK, and the CPK is the ratio that reflects how the process is performing, the actual performing, in terms of nominal, center, or target value. The CPK calculated by finding the minimum between these two values, which is the upper bound and the lower bound, upper specification limits minus the average divided by 3 sigma, or the average minus the lower specification limits divided by 3 sigma. Calculate the upper bound and the lower bound, then select the minimum. So this is the upper bound and this is the lower bound, the lower bound, and then take the minimum between them. If both are at least 1, then the process is capable. If one term is less than 1, the process is not capable. So if one of them is not less than 1, then the process is not capable. If one term is less than 1, the lower value tells you how it's shifted. If the lower value, the lower bound, is less than 1, that means the process is shifted to the left. If the upper bound value less than 1, means the process is shifted to the right. Okay, so it is very helpful calculation. The CPK will tell you if the process is centered or not. We need both of them. Both of them should be at least 1. At least if both of them at least 1. So this is at least 1, and then the process is capable. So the target that we're targeting is to be 1. Let's take a look into the chart. This hopefully will help you understand what the CP and the CPK. So assuming that we have upper specification limit here, and the lower specification limit is here, and here's the process. So the CP is A divided by B. This is A, the width of the specification, divided by the width of the process. The process itself. So if this is higher than 1, then the process is capable, and this is clearly known it's capable because this is too wide and this is only the width of the data. However, the CPK is C right here, the distance from here to here, divided by half of B, So divided by half of B. So that would be to figure out whether the process is centered or not. This is the smallest. C is the smallest of C or D. We pick whether the smallest between C or D, to making the CPK smaller when the process distribution is closer to the limits. Again, here this looks good, but it's not. It does not show how off the process. So we need the process is basically to be here somewhere, right here, 1 here and here. So that would be the centered of the process. However, this is capable, but there is a risk that the data will be shifted. The CPK is this is the smallest of C or D, which whatever is the smallest, and in this case, C is the smallest, divided by half of B, which is 3 sigma. So we're assuming 6 sigma for all the sigmas around the normal curve. Half of B, that would be 3 sigma. When the process distribution is centered within the limits, CP and CPK are equal. So when we know that the process is centered, when the CP equal to the CPK. CPK is how many sigma on the right and the left the normal distribution should be centered. All right, so how we interpret the CPK. So again, the target for you is to have it as a more than 1. This is your goal. If it's less than 1, then the process is not capable. But when interpreting the values of CPK, there are 3 significant regions. So this is And this is what we need to do. There are three significant regions which may be considered, and general rule is given in the table below. The value of a 3 as a total confidence limit may be lowered if measurements are taken as the average of a sample patches. Okay, less than 1, process is incapable. Improve by reducing common cause variation in the process variables. Use 100% inspection. You have to inspect every unit, every time. Between 1 and 3, the process is capable. So it's more than 1. So the process is capable. Do nothing or some process improvement. You could do nothing or some process improvement. Depends on the sample size. Maybe you need to have a bigger sample size. Greater than 3, very capable. Do nothing or reduce the specification limits. Maybe the specification, the tolerances is too loose. So maybe this is where you need to reduce the specification limit. No inspection necessary in this case. All right, the relationship, this is one of the last slides. So let's take a look into the relation between CP and CPK. When CP has a value of 1 or more or greater, the process is producing product capable of meeting specification. So the CP higher than 1, then the process is capable. CP value does not reflect the process centering. We don't know if the process is centered or not. It reflects the potential of the process. The process is centered when the CP equal to the CPK. So we do the calculation for CP and the CPK. If these two values are equal, then the process is centered. CPK is always less than or equal to the CP. That's a rule of thumb. If you have it more, then double check your calculation. When CP is greater than or equal to 1 and CPK has a value of 1 or more, it indicates, look at that, it indicates the process producing a product or service that conforms to the specifications. And that would be the target. We need the CP to be more than 1, CPK to be more than 1. When both more than 1, it means, so these are the case, that means the process is capable and it's performing well. So that's your target. When CPK has a value less than 1, it indicates the process is producing product that does not conform to specification. A CP value less than 1 indicates the process is not capable. A CPK value of 0 indicates the process average is equal to 1 of the specification limits. CPK with a negative value indicates that the average is outside the specification limits. All right, so now let's go ahead and apply some of what we have learned, and we'll take an example here. We'll take an example in just a second. All right, so taking a look into computing the CP value at the CocaViz, 3 bottling machines are being evaluated for possible use at the Fizz plant. The machines must be capable of meeting the design specification of 15.8 to 16.2 O's with at least a process capability index of 1. So we need to have a CP to be more than 1. Okay, so we have the table below shows the information gathered from production runs on each machine. So machine A, B, and C, the standard deviation is 0.05, 0.1 for B, and 0.2 for C. The difference between upper specification limits and lower specification limits is 0.4. And now for the 6, if we're going to apply this, upper specification limit minus lower specification limit, which is 0.4, divided by the 6 sigma, 6 times 0.5, 0.4 divided by 6 times 0.05, that will give you 1.3. That means the process is capable, potentially capable of meeting the customer need. Now we're going to do the CP for machine B and machine C, and I'm gonna let you work on that as well. Think about it and find out if the process is capable or not capable. So basically, what you need to do, you have to multiply 0.4 divided by 0.6. That is less than 1. This is the process is not capable. And then again, 0.4 divided by 1.2. Also, the process is not capable for machine B and C. Both of these are not capable. All right, the CPK design specification called for a target value of 16.2 or 16 minus 0.2 ounces. And this is what the upper specification 16.2, the lower specification is 15.8. Observe the process. The mean is 15.9, and that's the average. This is the standard deviation of 0.1. The CPK is less than 1. If you do the calculation, you will find that the CPK is less than 1. How would you do that? Again, find the minimum. Upper specification, you need to do the minimum between the upper specification 16.2 minus the average 15.9, divide that by 3 sigma. That's a 3. Or the minimum, the 15.8, the lower specification limit, or actually that should be the average minus the average, which is 15.9 divided by, or minus 15.9 minus 15.8, divide that by 3 times sigma, which is 0.01. And take the minimum between them, and you will see that the CPK is less than 1, so the process is not capable. The last thing that I want to conclude with is there is a one way to find out how to calculate the sigma level based on the CPK, and you use this equation. Sigma level is equal to the CPK times 3. So what we need to do, your target should be CPK to be 2 in order to have a 6 sigma process, which is that's the ideal target for any company. They are needed, they looking to achieve the 6 sigma process, which means 3.4 defects per million opportunity. All right, I'll see you in another video. I will take Excel sheet example now to verify that you understand the CP and the CPK. We'll take an actual case study from real life, and we will see how we could calculate the CP and the CPK. But with that said, I would like to thank you for watching me, and I will see you in another video using Excel and how we could find the CP and the CPK. Thank you.